we'll be going through chapter 14 of Computer Organization and Architecture. Let us consider the requirements placed on the processor. The things it must do. Fetch instruction. The processor reads an instruction from memory, register cache, main memory. Interpret instruction. The instruction is decoded to determine what action is required. Fetch data. The execution of an instruction may require reading data from memory or an I/O module. Process data. The execution of an instruction may require performing some arithmetic or logical operation on data. Write data. The results of an execution may require writing data to memory or an I/O module. The five steps of process organization are as follows. First step is fetch instruction. The processor reads an instruction from memory, register cache. Reading data from memory or an I/O module. The third step some arithmetic or logical operation on data. The final step is to write the data your module. To do these things, it should be clear that the processor needs to store some data temporarily. Remember the location of the last instruction so that it can know where to get the next instruction. It needs to store instructions and data temporarily while an instruction is being executed. In other words, the processor needs a small internal memory. Figure 14.1. Let's look at figure 14.1. So 14.4. And this is figure 14.1. Figure 14.1 is a simplified view of a processor indicating its connection to the rest of the system via the system bus. This is a simplified view of our system and it indicates its connection to the rest of the system via the system bus. So via the system bus indicates its connection to the rest of the system. A similar interface would be needed for any of the interconnection structures described in chapter 3. The reader will recall that the major components of the processor are an arithmetic and logic and a control unit. The ALU does the actual computation processing of data. The control unit controls the movement of data and instructions into and out of the processor and controls the operation of the ALU. In addition, the figure shows a minimal internal memory consisting of a set of storage locations. The control unit controls the movement of data and instructions into and out of the processor and controls this control unit controls the movement of data and instructions into and out of the processor. It controls the movement of data and instructions into and out of the processor and controls the operation of the ALU. It controls the operation of the control unit controls the operation of the ALU. In addition, the figure shows minimal internal memory consisting of a set of storage locations called registers. So this is the minimal internal memory, which is known as registers. It's a set of consisting of set of storage locations called registers. These registers are basically small storage locations. There's a control bus, there's a data bus, and there's an address bus. Figure 4.2 is a slightly more detailed view of the processor. This is a slightly more detailed view of the processor. Data transfer and logic paths are indicated, including an element labeled internal processor bus. This is the internal CPU bus. The data transfer and logic control paths are indicated. Data transfer. So data transfer happens through these lines. So data transfer and logic paths are all these lines, including an element labeled internal processor bus, and this is the internal processor bus, also known as the internal CPU bus here. This element is needed to transfer data between the various registers and the ALU because the ALU in fact operates only on data in the internal processor memory. So the internal CPU bus is required to transfer data between various registers. So this is required to transfer data between various registers. These are the registers here. Between various registers, transferring of data happens through the internal CPU bus. And also within the ALU. So this is the entire ALU, and within the ALU, transfer of data or control signals happens through the internal CPU bus. ALU in fact operates only on data, and only data gets transferred uh, through the ALU. The figure also shows typical basic elements of the ALU. Note the similarity between the internal structure of the computer as a whole and the internal structure of the processor. In both cases, there is a small collection of major elements: computer processor, IO memory, processor, control unit, ALU, registers. There's a small collection of major elements connected by data paths. Register organization. Okay, as we've discussed, computer system employs a memory hierarchy. At higher levels of the hierarchy, memory is faster, smaller, and more expensive. At higher levels of the hierarchy, memory is faster, smaller, and more expensive. Within the processor, there is a set of registers that function as a level of memory above main memory and cache in hierarchy. Within the processor, there is a set of registers that function as a level of memory above main memory and cache in the hierarchy. The registers in the processor perform two roles. User visible registers enable the machine or assembly language programmer to minimize main memory references by optimizing use of registers. User visible registers enable the machine or assembly language programmer to minimize main memory references by optimizing use of registers. Control and status registers used by the control unit to control the operation of the processor and by privileged operating system programs to control the execution of the programs. The register in the processor major roles of the registers in the processor are as follows. User visible registers enable the machine or assembly language programmer to minimize main memory references. So the first use is for the application programmer, uh, assembly level programmer, where he can use these registers uh, as a form of memory instead of the cache. So you will be reducing your accesses to cache by using a smaller, closer form of memory to the CPU, to the processor, which is the user visible registers. The other function of registers is control and status registers. used by the control unit to control the operation of the processor and by privileged operating system programs to control the execution of programs. So the other function of register is to is for control and status. So it is used by the control unit to control the operation of the processor. Um, so the other use of registers is uh, by that of the control unit. Control unit to control the operation of the processor and by privileged operating system programs to control the execution of the program. There is not a clean separation of registers into these two categories. For example, on some machines, the program count is visible, but many it is not. For purposes of the following discussion, use these categories. User visible registers. A user visible register is one that may be referenced by means of the machine language that the user visible register is defined as a register that may be referenced by means of a machine language that the process executes. We can characterize these in the following categories: general purpose registers, data registers, address registers, and condition codes. General purpose registers can be assigned to a variety of functions by the programmer. Okay. General purpose registers can be assigned to a variety of functions by the programmer. Sometimes their use within the instruction set is that is any general purpose register can contain the operand for any opcode. Okay, so you're storing operands in general purpose registers. This provides true general purpose register use. Often, however, there are restrictions. For example, there may be dedicated registers for floating point and stack operations. For example, there may be dedicated registers for floating point and stack operations. Okay. In some cases, general purpose registers can be used for addressing functions. Example, register indirect displacement. In other cases, there is a partial or clean separation between data registers and address registers. In some cases, general purpose registers can be used for addressing functions. Example, register indirect displacement. In other cases, there is a partial or clean separation between data registers and address registers. Data registers may be used only to hold data and cannot be employed in the calculation of an operand address. Some cases, general purpose registers can be used for addressing functions. Example bit example indirect register indirect displacement. So again, we have general purpose registers, data registers, address registers, and condition codes. So here they're telling that general purpose registers can be used for addressing functions. Example register indirect. In other cases, there is a partial or clean separation between data registers and data registers may be used only to hold data and cannot be employed in the calculation. Address registers may themselves be somewhat general be devoted to a particular address. Registers can be general purpose or they may be devoted to a particular addressing mode. Examples include the following: segment pointers. In a machine with segmented addressing, A segment register holds the address of the base of the segment. There may be multiple registers, for example, one for the operating system, one for the current process. So I don't know what segmented addressing is. We'll look into it later. Index registers, they are used for indexed addressing and may be auto-indexed. Index addressing is, let's say you're iterating through an array and the index value can be stored here in an index register. I equals 0 to I equals n minus 1. That value of I you can store in the index register. Stack pointer, if there is user visible stack addressing, then typically there is a dedicated register that points to the top of the stack. Okay, so there's a register that always also points to the top of the stack that stores the address which points to the top of the stack. This allows implicit addressing, that is, push, pop, and other stack instructions need not contain an explicit stack operand. This allows implicit addressing. Push, pop, and other stack instructions need not contain an explicit stack operand. There are several design issues to be addressed here. An important issue is whether to use completely general purpose registers or to specialize their use. An important issue is whether to use completely general purpose registers or to specialize their use. An important issue is whether to use completely general purpose registers or to specialize their use. We have already touched on this issue in the preceding chapter because it affects instruction set design. With the use of specialized registers, it can generally be implicit in the opcode which type of register a certain operand's specifier refers to. The operand specifier must only identify one of a set of specialized registers rather than one out of all the registers, thus saving bits. On the other hand, this specialization limits the programmer's flexibility. Let's see what is this that they're talking about. Okay, let's just move on. Another design issue is the number of registers, either general purpose or data plus address, to be provided. Again, this affects the instruction set design because more registers require more operand specifier bits. So as we increase the number of registers, we need more bits to represent, uh, to address these registers or to know to find out which register that we are trying to access. So as we previously discussed, somewhere between 8 and 32 registers appear in optimum. Fewer registers result in more memory references. More registers do not noticeably reduce memory references. However, a new approach which finds advantages in the use of hundreds of registers is exhibited in some RISC systems and is discussed in chapter 15. Finally, there is the issue of register length. Registers that must hold addresses obviously must be at least long enough to hold the largest address. So, and data registers should be able to hold values of most data types. Some machines allow two contiguous registers to be used as one for holding double length values. A final category of registers, which is the least partially visible to the user, holds condition codes, also referred to as flags. So the final category of registers holds the condition codes, which are also called flags. Condition codes are bits set by the processor hardware as the result of operations. For example, an arithmetic operation may produce a positive, negative, zero, or overflow result. In addition to the result itself being stored in a register or memory, a condition code is also set. The code may subsequently be tested as part of a conditional branch operation. Condition codes are bits set by the processor hardware as a result of operations. For example, an arithmetic operation may produce a positive, negative, zero, or overflow out result. In addition to the result itself being stored in a register or memory, a condition code is also set. The code subsequently be tested as part of a conditional branch operation. Let's look into this later. Condition code bits are collected into one or more registers. Usually they form part of a control register. Generally, machine instructions allow these bits to be read by implicit reference, but the programmer cannot alter them. Many processors, including those based on the IA64 architecture and the MIPS processors, do not use condition codes at all. Rather, conditional branch instructions specify a comparison to be made and act without storing a condition code. Table 14.1, based on this paper, lists key advantages and disadvantages of condition codes. Okay, let's go to page 493. Codes advantages. Because condition codes are set by normal arithmetic and data movement instructions, they should reduce the number of compare and test instructions needed. Condition codes add complexity both to the hardware and software. Condition code bits are often modified in different ways by different instructions, making life more difficult for both the microprogrammer and compiler writer. Conditional instructions such as branch are simplified relative to composite instructions such as test and branch. Condition codes are irregular. They are typically not part of the main data path, so they require extra hardware connections. Condition codes facilitate multi-way branches. For example, a test instruction can be followed by two branches, one on less than or equal to 0 and one on greater than 0. Often condition code machines must add special non-condition code instructions for special situations anyway, such as bit checking, loop control, and atomic semaphore operations. Condition codes can be saved on the stack during subroutine calls along with other register information. In a pipeline implementation, condition codes require special synchronization to avoid conflicts. There's no way I'm going to remember advantages and disadvantages. In some machines, a subroutine call will result in the automatic saving of all user visible registers to be restored on return. The processor performs the saving and restoring as part of the execution of call and return instructions. This allows each subroutine to use the user visible registers independently. On other machines, it is the responsibility of the programmer to save the contents of the relevant user visible registers prior to a subroutine call by including instructions for this purpose in the program. Control and status registers. There are a variety of processor registers that are employed to control the operation of the processor. Most of these on Most machines are not visible to the user. Some of them may be visible to machine instructions executed in a control or operating system mode. Of course, different machines will have different register organizations and use different terminology. We list here a reasonably complete list of register types with a brief description. Four registers are essentially Four registers are essential to instruction execution: program counter, instruction register, memory address register, memory buffer register. Program counter contains the address of an instruction to be fetched. Instruction register contains the instruction most recently fetched. Memory address register contains the address of a location in memory. Memory buffer register contains a word of data to be written to memory or the word most recently used. Not all processors have internal equivalent buffering mechanism is needed, whereby the bits to be transferred to the system bus are staged and the bits to be read from the data bus are temporarily stored. Typically, the processor updates the PC after each instruction fetch so that the PC branch or skip instruction will also modify the contents of the PC. The fetched instruction is loaded into an IR where the opcode and operand specifiers are analyzed. Data exchange with memory using the memory address register and memory buffer register. In a bus organized system, the memory address register connects directly to the address bus. The memory buffer register connects directly to the data bus. User visible registers in turn exchange data with the memory buffer register. Address of instruction to be fetched. Instruction register contains the instruction most recently fetched. Memory address register contains the word most recently read. Not all processors have internal registers designated as memory address register, memory buffer register, but some equivalent buffering mechanism is needed whereby the bits to be transferred to the system bus are staged and the bits to be read from the data bus are temporarily stored. Typically, the processor updates the program counter after each instruction fetch so that the PC always spawns to the next instruction to be executed. A branch or skip fetch instruction is loaded into the instruction register where the opcode and operand specifiers are analyzed. Data are exchanged with memory using the memory address register and memory buffer register. In a bus organized system, the memory address register connects directly with the address bus. In a bus organized system, the memory address register connects directly to the address bus and the memory buffer register connects directly to the data bus. User visible registers in turn exchange data with the memory buffer register. The four registers just mentioned are used for the movement of data between the processor and the memory. With the processor, data must be presented to the ALU for processing. The ALU may have direct access to the memory buffer register and user visible registers. Alternatively, there may be additional buffering registers at the boundary of the arithmetic logic unit. These registers serve as input and output registers for the arithmetic logic unit and exchange data with the memory buffer register and user visible registers. Many processor designs include a register or set of registers, often known as the program status word (PSW), that contain status information. The PSW typically contains condition codes plus other status information. Common fields or flags include the following. Many processor designs include a register or set of registers, often known as the program status sign contains the sign bit of the result of the last arithmetic operation. 0. Set when the result is 0. Set if an operation resulted in a borrow suppression out of a high order bit used for multi-word arithmetic operations. Equal set if a logical compare result is equality. Overflow used to indicate enable disable used to enable or disable interrupts. Supervisor indicates whether the processor is executing in supervisor or user mode. Certain privileged instructions can be executed only in supervisor mode, and certain areas of memory can be accessed only in supervisor mode. A number of other registers related to status and control might. There may be a pointer to a block of memory containing additional status information. Instruction cycle in section 3.0 we describe the process instruction cycle. To recall, read the next instruction from memory into the processor. Interpret the opcode and perform the indicated operation. Interrupt. If interrupts are enabled and an interrupt has occurred, save the current process state and service the interrupt. We are now in a position to elaborate somewhat. First, we introduce one initial stage known as the indirect circle. The indirect cycle, as we have seen in chapter 13, the execution of an instruction may involve one or more operands in memory, each of which requires memory access. Further, if indirect addressing is used, then additional memory accesses are required. We can think of fetching of indirect addresses as one more instruction stages. The result is shown in figure 14.4. Fetch, either execute or indirect, and from indirect goes to execute. From execute, it can go to the to interrupt, or it can go to fetch. Main line of activity consists of alternating fetch and instruction execution activity. After an instruction is fetched, it is examined to determine if any indirect addressing is involved. If so, the required operands are fetched using indirect addressing. Following execution, an interrupt may be processed before the next instruction. Following execution, an interrupt may be processed before the next instruction fetch. Another view to view this process is shown in figure 14, the revised version of figure 3. Instruction cycle state diagram. So you have interrupt check, interrupt. Okay, it's very complex. Instruction address calculation. Instruction fetch. Once instruction is fetched, instruction operation decoding. Instruction decode, instruction fetch, instruction decode. Operand address calculation. So fetching data items. So to fetch the data items, you calculate the address of where the operand is present. Then operand fetch, you fetch the operand from the uh, address of wherever it's located in the memory. And then indirection will further do it will whatever you find in the memory, it'll direct you to another address where the operand is present. So from there you get the operand, and then multiple operands are brought and done. And so yeah, once that happens, you go to the next step, which is the data operation. So you have the operand values. Now you uh, data operation. What's data operation? Okay, data operation is the operand address. Okay, data operation is the addition or multiplication or subtraction that is to be performed. So that data operation will be done among the two operands. And once you obtain a result, operand address calculation. So once you obtain a result, where should that result be stored? You calculate the address of where the result is to be stored. So once you do the operand address calculation, you do the operand store. Again, even in this case, you can have an indirection uh, uh, instruction where you point to one address and then that address will contain the address of where the operand is to be stored. So you'll have some indirection there. You might or might not have it. So if you have it, then there will be a for there this operand store will happen twice. Uh, and then interrupt check. So once this instruction is performed, you check if there is any interrupt. If there is any interrupt, you address the interrupt. If there's no interrupt, you continue, and then you find the next instruction. Instruction complete, fetch next instruction. So what is this thing? Return for string or vector data? I don't remember. The indirect cycle. We have seen in chapter 13 that the execution of an instruction may involve one or more operands in memory, each of which requires a memory access. Further, if indirect addressing is used, then additional memory is required. We can think of fetching of indirect addresses as one more instruction stages. This result is shown in figure 14.4. Data flow. The exact sequence of events during an instruction cycle depend on the design of the processor. We can indicate in general terms what must happen. Let us assume that a processor that employs a memory address register, a memory buffer register, a program counter. During the fetch cycle, an instruction is read from memory. During the fetch cycle, instruction is read from memory, shows the flow of data during this cycle. Flow of data shown during this cycle. The PC contains the address of the next instruction to be fetched. This address is moved to the memory address register and placed on the address bus. So the next address to be fetched is put into the memory address register, and then that address is then put into the address bus.
What they say? First what the first what they said.
Data flow. The exact sequence of events during an instruction cycle depends on the design of the processor. We can, however, indicate the general terms. We can, however, indicate in general terms what must happen. Let us assume that a processor that employs a memory address register, a memory buffer register, program counter, and an instruction register. During the fetch cycle, an instruction is read from memory. During the fetch cycle, an instruction is read from memory. Figure 14.6 shows the flow of data during this cycle. Figure 14.6 shows the flow of data during this cycle. The PC contains the address of the next instruction to be fetched. PC contains the address of the next instruction to be fetched. This address is moved to the memory address register and placed on the address. Control unit requests a memory read. The result is placed on the database. The result is placed on the data bus and copied into MBR. Control requests a memory read. The result is placed into MBR and then moved to the IR. Once the fetch cycle is over, the control unit the rightmost n bits of uh, memory buffer register which contain the address reference are transferred to the memory address register. Then the control unit requests a memory read. To get the desired address of the operand. Memory will send into the database. Fetch and indirect cycles are simple and predictable. The execute cycle takes many forms. The form depends on which of the various machine instructions is in the instruction register. The cycle may involve transferring data among registers, read or write from memory or IO, and or the invocation. which are indirect cycles. The interrupt cycle is simple and predictable. Another example of a resource conflict is a situation in which multiple instructions are ready to execute instruction phase and there is a single ALU. One solution to such resource hazards is to main memory and multiple ALU units. One approach to analyzing resource conflicts and another example of resource conflict is a situation in which multiple instructions are ready to enter the execute instruction phase and there is a single ALU. One solution to such resource hazard is to increase available resources such as having multiple ports into main memory and multiple ALU units. One approach to analyzing resource conflicts and aiding in the design of pipelines is the reservation table. We examine reservation tables in Appendix N. Data hazards. A data hazard occurs when there is a conflict in the access of an operand location. In general terms, we can state the hazard in this form. Two instructions in a program are to be executed in sequence and both access a particular memory or edge to operand. If the two instructions are executed in strict sequence, no problem occurs. However, if instructions are executed in a pipeline and it is possible for the operand value to be updated in such a way as to produce a different result than would occur with strict sequential execution. In other words, the program produces an incorrect result because of the use of pipelining. As an example, consider the following x86 machine instruction sequence. Add EAX, EBX. So EAX equals EAX plus EBX. Subtract ECX, EAX. So ECX equals ECX minus EAX. The first instruction adds the contents of the 32-bit registers EAX and EBX and stores the result in EAX. Second instruction subtracts the contents of EAX from ECX and stores the result in ECX. Figure 14.16 shows the pipeline behavior. Add EAX, EBX. Subtract ECX, EAX. So this area has to be idle because because there is a data hazard. There are three types of data hazards: read after write or true dependency. An instruction modifies a register or memory location and a succeeding instruction reads the data in that memory or register location. A hazard occurs if the read takes place before the write operation is complete. Write after read dependency or anti-dependency. An instruction reads a register or memory location and a succeeding instruction writes to the location. A hazard occurs if the write operation completes before the read operation takes place, write after write dependency or output dependency. Two instructions both write to the same location. A hazard occurs if write operation takes place in the reverse order of the intended sequence. The other two hazards are best discussed in the context of a superscale organization discussed in chapter 16. Control hazard, the control hazard, also known as a branch hazard, occurs when pipeline makes the wrong decision on a branch prediction, therefore brings instructions into the pipeline that must subsequently be discarded. We discuss approaches to dealing with control hazards next. Dealing with branches, one of the major problems in designing an instruction pipeline is assuring a steady flow of instructions to the initial stages of the pipeline. The primary impediment, as we have seen, is the conditional branch instruction. Until the instruction is actually executed, it is impossible to determine whether the branch will be taken or not. A variety of approaches have been taken for dealing with conditional branches. Multiple streams, prefetch, branch target loop buffer, branch prediction, delayed branch. Multiple streams. A simple pipeline suffers a penalty for a branch instruction because it must choose one of two instructions to fetch next and may make the wrong choice. A brute force approach is to replicate the initial portions of the pipeline and allow the pipeline to fetch both instructions, making use of two streams. There are two problems with this approach. Multiple pipeline operations, there are contention delays for access to the registers and to memory. Additional branch instructions may enter the pipeline by the stream before the original branch decision is taken. Each such instruction needs an additional stream. Despite these drawbacks, the strategy can improve performance. Examples of machines with two or more pipeline streams are IBM 370-168 and IBM 3033.